Okay, so now it's time to look at number 8. So these are improper integrals. So we need to be careful about writing things as limits and such. But other than that, it's not the worst thing in the world. So A, look at the integral from 1 to infinity of dx over x. I'm going to go ahead and prefactor here, x times x plus 2. So now we have to actually know how to integrate these. So let's think about it. We have 1 to infinity, and we have a fraction where the denominator is a polynomial. So that makes me think partial fractions. And actually, you might notice this is literally the same partial fraction we did in 7, but that's okay. So equals integral 1 over to infinity a over x plus b over x plus 2 dx. And now let's push forward a little bit, do this partial fractions pretty quickly. I get 1 is equal to a times x plus 2 plus b times x. So if x is minus 2, then I get 1 is equal to minus 2b, because the a goes to 0. So b is minus 1/2. If x is 0, 1 equals 2a, so a is equal to 1/2. So then this guy is the integral from 1 to infinity of, both of these are a 1/2 term, but let's wait on that. 1 over 2x plus, and by plus I mean minus, 1 over 2x plus 2 dx. Again, really these are 1/2s in the numerator, but if you have a 1/2 in the numerator, you can kind of pull that fraction down. And so this is this. Now I'm going to put out a 1/2, integral 1 over x minus 1 over x plus 2 from 1 over x to from integral 1 to infinity of this equals 1/2 natural log of x minus natural log x plus 2 evaluated from quote unquote 1 to infinity, but we have to remember what that means. This is the limit as b goes to infinity, or t, 1/2 natural log of x minus natural log of x plus 2 from 1 to b. All right. So first, if I plug in b, I get natural log of b minus natural log of b plus 2. Does that do anything? I don't really know. But I have logs here and I have minus. So this is actually limit b goes to infinity of 1/2 the natural log of x over x plus 2, right? Because of log rules, log of something minus log of something just says divide those things. Now I can push this limit in. Evaluated from b to 1. So this is 1/2. Let's put the 1/2 out of the limit. Limit b goes to infinity. Plugging in, we get natural log of b over b plus 2 minus natural log of 1 over 1 plus 2. That's natural log of 1/3. That's not going to make a difference on whether this converges or not. But let's see. So as b goes to infinity, this is 1/2 limit b goes to infinity, or, oops. I can put this limit on the inside. Natural log of the limit as b goes to infinity, b over b plus 2 minus the natural log of 1/3. So as b goes to infinity, then absolute value of b over b plus 2 is going to be going to 1. b over b plus 2 goes to 1. So this is 1/2 natural log of 1 minus natural log of 1 over 3. The 1 goes away, so this is 1/2 minus natural log of 1/3. Or I could also write this 1/2 natural log of 3 using log rules. So that's part A. And you really do need to write these limits as b goes to infinity when you do this, otherwise you're going to be in trouble. Definitely lose points at the very least. So now let's go to B. This is integral from 0 to infinity of 3p squared dp over the square root of 1 plus p cubed. So how do I do an integral like this? Again, don't default to trig substitution too quickly, because we can instead let u be 1 plus p cubed, in which case du is 3p squared. And now u of, let's start with 0, that's 1. So I have u of 1, u of quote-unquote infinity, if I try changing bounds. That's going to be infinity. So what does that mean? What am I doing? If limit, or I want to say it this way, if 1 plus p cubed, nope. If p is going to infinity, 1 plus p cubed is going to infinity. So that's the explanation for why we're allowed to sub in like this. Or saying it in adult math terms, limit as p goes to infinity of p implies limit as b goes to infinity of p cubed plus 1 is infinity. So that's why we can make that change of bounds like that. Be careful, because sometimes you might have a bound that goes to infinity, but if you do a u sub, say like 1 over x, if x goes to infinity, 1 over x goes to 0. So you don't always get infinity back, and that's all I'm trying to say there. So now we have du over the square root of u equals integral 1 to infinity u to the minus 1/2 du. And so now I get u to the 1/2. What do I put here? 1/2, but flip it, so 2. Evaluate that from 1 to infinity. But what does that mean? This is now the limit as t goes to infinity of 2, and then t to the 1/2 minus 1 to the 1/2. But as t goes to infinity, this thing equals infinity. So specifically, you should say the integral diverges to infinity. So this is not a good integral. It doesn't make sense. It's too big. Next, I can fit this one. C integral from minus infinity to infinity of 1 plus x squared plus 1 dx. So this one looks really spooky, but that's okay. Because first, this integral is just tan inverse of x evaluated. Well, by definition, we can pick some number between these. So 1 over x squared plus 1 integrals 0 to minus infinity. 1 over x squared plus 1 dx. Again, this was the definition. You pick some number between infinity and 0. Doesn't matter which one. Or infinity and minus infinity. Doesn't matter which one. I'll pick 0 because it's nicest. But it doesn't matter. And now this is tan inverse of x evaluated from 0 to infinity plus tan inverse of x evaluated from 0 to minus infinity. And so this is going to be the limit as b goes to infinity of tan inverse of b minus tan inverse of 0 plus limit as a goes to minus infinity of tan 0 inverse tan inverse of a. So these tan inverses of zeros don't depend on the limit, so they can cancel. As b goes to infinity, tan inverse of b goes to pi over 2. That's a fact that we know. And then tan inverse of a as a goes to minus infinity. So minus pi over 2, or we end up with pi. And so that's our final answer there.